Okay, welcome back. So we'll start a new lecture series today by Professor Kandaswamy Subramanian, or Kandu as he's fondly referred to by everyone who knows him. So it's really nice to have Kandu here. He has been at IUCA for many years. Before that he was at NCRA and before that at TIFR. And Kandu is one of those people who has worked on everything in cosmology. Right? So starting from gravitational lensing, cosmic microwave background, structure formation, galaxy evolution, magnetic fields, and then since the last, 10 years or so, this has been his pet thing of all possible varieties of magnetic fields, from primordial down to stellar, ISM, etc. So apart from the topic of the lecture, which is galaxy formation, in which you will probably see many of these aspects, I encourage you all to catch him over the tea breaks and the lunch breaks and generally chat with him. So,
wow. I'm impressed. So it's nice to see so many young faces in the audience, all waiting to hear about the dirty business of galaxy formation. And it's kind of Aseem who has been encouraging me to keep talking about this at various places. So you probably would have heard a lot about, at present, galaxies in terms of structure formation, in terms of the dark matter, in terms of perturbation theory. And most of that is fairly clean physics in the sense that initial conditions are nicely laid out. Evolution is very nice to follow, linear perturbation theory, some nice exact models, and also some predictions from either the CMB or large-scale velocity fields, or nowadays 21 centimeter. But finally, if you're thinking about galaxy formation, you're interested in actually galaxies. Galaxies means a bunch of stars with some typical masses, some typical properties. And from all this stuff that we learn about with dark matter, evolution, etc., question is, how do galaxies form? And that's the main topic that I'm going to concentrate on in the next today and 2 lectures tomorrow. And I'm going to give you a flavor of many of the physical processes that are involved. I'm not myself a great simulator of anything, so I don't do numerical simulations. And I've done some analytic stuff, but there are a lot of interesting physics going on. And all of them go to determine various properties of the galaxy that we see today. And that's what I want to concentrate on. So this is a standard picture taken from Springle and Hernquist long time back. And you'll see some of my slides will be as aided as I will be. But the physics has not changed. And small perturbations growing into all the structures that we see today. And the stuff that we are really interested in when we are talking about galaxies, and this is also very old, of course, from the time of Hubble, that there are things which we call galaxies, which are different from stars, which are different from clusters of galaxies that you have already heard about. The main difference, if you look at some properties, is that they may have about 100 billion stars, roughly. It could be smaller, 10 times smaller, 10 times larger at the best. They have a total mass. For example, if you take our Milky Way, probably the total mass in the Milky Way is about 10 to the 12 solar masses, maybe 10 times larger than the stellar mass. And we think that this is made out of a dark halo, dominated by a dark matter halo, in which the luminous galaxy is sitting somewhere in the center, because the dark matter halo of a typical Milky Way type galaxy of 10 to the 12 solar mass has a radius of about 100 kiloparsec, roughly, a virial radius or a bound radius. And the galaxy itself is within a few tens of kiloparsec. So it's like there's a big ball and in the center a small dosa with an idli sitting in the bulge in the middle. When you can see that the analogy you can learn from others. So with a small disk, okay? And sizes of 10 kiloparsec. And there are various kinds of galaxies, mainly the main kind divided into two classes. One, for example, which are more or less round, called elliptical galaxies. The other, which are called spirals because they show prominent spiral patterns, but more correctly, disk galaxies. And the difference being the ellipticals are mostly having their stars moving randomly about and supported by the dispersion, velocity dispersion of the stars in the potential well, whereas the disk is basically supported by the rotation of the disk and very flat. And among spirals, there will be guys which have developed prominent bar-like structures in the center called barred spirals. And this is an old diagram called the tuning fork diagram of Hubble, which shows both these types of galaxies. The question that one is interested when you're thinking about galaxy formation is what determines that there should be a bunch of a system like this, which has got a mass of about 10 to the 11, 10 to the 12 times the mass of the sun, having radius like this, with a dark matter halo. Why these two different types of galaxies? Why? What sets the mass scale, the length scale, and the properties that you have of galaxies that you see today, from all the stuff that you see in the dark matter distribution. So these are some of the issues that I will be discussing in the next 3 lectures. I will talk a little bit about cooling. So all of them involve stuff to do with baryons, firstly. I'm taking for granted that you have all been completely well educated in the dark matter side. Yeah? And you're all experts on dark matter, perturbation, evolution to nonlinear stages, collapse, and you have a nice dark matter halo. And then there is baryons, which is there, and this is going to collapse, heat up, and you have to heat to cool. And I'll explain this slightly contradictory statement. The cooling of the gas, setting galactic masses, the collapse to form stars, star formation. One of the main issues of galaxy formation is star formation. Now you may think star formation, chalo, I'm a cosmologist. Stars are those guys which I should forget about. But that's absolutely the thing which is preventing people completely from understanding galaxy formation, because star formation is actually a very complicated subject. And exactly like how we are thinking about what sets the mass scale for galaxies, what sets the mass scale for stars is an equivalent question, which is an extremely interesting question. So I'll talk a little bit about star formation. Then once stars form, the feedback from stars on galaxy formation and star formation. I'll say some other stuff about active galaxies. And I can't avoid talking about magnetic fields, as Aseem has said. But I'll also talk more about cosmic rays. Then I will say something about formation of disk galaxies, elliptical galaxies. And I may finally, if I have time, come to some of the stuff that we have done now already some time back with a couple of students at IUCA on understanding high redshift galaxy abundance and clustering. So this is the plan that I have. So let's get into it. So this is the structure formation timeline that you all know and love, that you start from some early stage in the universe, where there's supposed to be something like inflation, which generated fluctuations in the potential. There were small perturbations. And it's also absolutely intriguing that these are supposed to have come from some quantum zero-point fluctuations and developed into all the stuff that we see today. That's a different subject by itself. They are reflected in the microwave background anisotropy, and they're also reflected in the large-scale structure. These small fluctuations grew by gravity. Gravitational instability was the reason for which the fluctuation that you originally had grew, and they grew to form all the nonlinear structures that we see today. So you start with a small density of potential fluctuation. Then the universe is expanding because the gravity of this is attracting all the stuff together. This region, which is, let's say, overdense, stops expanding, freezes, turns around, and collapses back. virializes, and this is something which you may have heard already, forms an object that you see, which you call a dark matter halo. And then you, at some stage, have to form stars and galaxies. And the first stars is also related to a very important part of the story, which is the reionization of the universe. And nowadays, it's also playing a very prominent role in discussing 21 centimeter signals from there. Then, as far as the dark matter halo is concerned, or dark matter evolution is concerned, what you have is bigger and bigger structures all the time collapsing. So we are thinking about the model, the favored model, which is the Lambda CDM model, where the dark matter is made out of cold dark matter, and the universe is dominated by some kind of dark energy today, but in the past it was matter dominated by this cold dark matter. There were initial fluctuations, and there is one scale which is set because at the time of matter radiation equality, okay, there is a scale which is set on this power spectrum, but otherwise there's no scale. There is a complete, at the smallest possible scales, the fluctuations become nonlinear first, they collapse, then bigger scales collapse, then bigger scales collapse, until, for example, today, the bigger scales which have collapsed are the rich clusters of galaxies. So in this whole hierarchy, the question is what sets the mass scale of galaxies? If you look at a cluster of galaxies, galaxy cluster, it's supposed to have a lot of hot gas. I think you've already heard a talk on this, which is emitting in X-rays. Okay? But it doesn't have 10 to the 14 solar mass of stars. Right? It has galaxies which are all themselves have 10 to the 11 solar mass stars, let's say, all embedded in this big rich cluster. So the cluster gas obviously has not all turned into stars. Whereas a significant fraction of the galaxy gas has turned into stars. So what sets this mass scale, and how does this galaxy of stars form in this whole timeline that we are thinking about? So this is the standard stuff. It's the same timeline going through, and you have all these structures which are formed. So let me not get into that too much. Maybe you have seen this also, I guess, right? It's an abused cow, poor guy, should complain to something of harassment. If there's a cow too movement or something like that. But so this is the simplest model that we have for collapse. Okay? And I think Aseem must have gone through it in some detail. That you imagine, the reason I'm mentioning it again, it's a thing which you can start off even thinking about baryonic physics. So you have a region which is spherically overdense, and then you allow it to collapse, and you follow its evolution. So this is a spherical collapse model, pretty straightforward and simple to analyze, and that's why it's so useful. And it does have certain degree of truth. And of course, you have to be always careful about what it doesn't have. So in this model, we start with a spherically overdense region and follow its evolution. And one finds that it obeys a simple Newtonian type of equation. Acceleration is gm by r squared, which you can solve parametrically in terms of a parameter theta. So r is 1 minus cos theta and t is theta minus sine theta, with constants which can be related, and a density contrast which you can easily work out. And what you find in this model, I'm not getting into detail because I guess it must be worked out in great detail. I think you worked it out, right? Is that you find that this spherically overdense region, if you treat it, let's say, as a top hat overdense region, expands with the universe to begin with because the density fluctuations are small. At some stage, freezes so that it stops expanding. And that stage is called the turnaround. Okay? At that stage, the peculiar velocity is 0. Then it collapses. It collapses. It stops expanding when r is maximum and theta is pi. When the density contrast, which you can work out from here, is this number 5.6. You can change all this if you introduce the cosmological constant a little bit, but not greatly. And then it collapses back at theta equal to 2 pi at r equal to 0. But of course, nothing goes to r equal to 0 because that's, so it's something else will happen. For the dark matter, it must be the virialization of the dark matter to form this collapsed bound dark matter halo. This itself is an extremely interesting, complicated, ununderstood subject. I mean, one can spend a lot of time just discussing collisionless virialization because you have dark matter particles which are cold dark matter, weakly interacting. They're not going to collide, they're collisionless. A huge number of them, they come and settle down to some hydrostatic type equilibrium, but they're not gas. They have velocity dispersion, they don't have pressure. So how did they reach this almost thermal distribution? It's almost thermal because they're not exactly thermal. Thermal would have meant isotropic velocity dispersions also. In case of dark matter, it's anisotropic. In fact, the system are not spherical mostly. From the simulation, you'll find they're triaxial typically. They have typical density profiles which have been made famous by Navarro, Frank, and White. And we don't know exactly, but that's a big story by itself. It's an interesting story, not for today. But the gas is simpler. What it does, it collapses, and it's cold to begin with, typically. You can imagine that the gas started off in equilibrium with radiation at some early epoch. Then when recombination occurred, okay, at about 3000 degree Kelvin, the gas was also around at 3000 degree Kelvin. Then photons decoupled from the rest of the matter. So everything was free streaming. The photons were free streaming, the baryons were free streaming. But there is a residual ionization. It's not, when recombination is not something where you get 0 electrons at the end of the day. And this is something I think which you'll hear about more in later lectures. That residual ionization is sufficient to keep the baryons and the photons coupled for until redshifts about 100 or so. So the temperature goes down with expansion just like the photons. So from 3000, it may go to about few hundred degree Kelvin. Then the density was low enough that even this was not sufficient. So now the baryons are non-relativistic, like protons, electrons and all, and they decouple from the radiation. So with expansion, their momenta goes down as 1 over expansion factor. For non-relativistic particle, the energy is p squared. So the kinetic energy goes down as 1 over expansion factor squared. So now they cool much faster than the radiation. So by redshifts, let's say about 10, they are fairly cold. And then they are at some stage, the gravitational potentials are also growing. Bigger and bigger objects are collapsing. And this gas, the baryons, at some stage, they can be captured into these potentials. When they're captured, they will collapse. Now they're cold and they will free fall. When gas moves faster than its sound speed, shocks will develop. And when you have shocks, you will get the gas heated again. So there will be this hot gas typically in these potential wells. And you can make some estimates of this. Okay, this I think you would have seen before. You can make some simple estimates. For example, from virial theorem, one knows that the kinetic energy is half the potential energies minus the total energy for the dark matter. So you expect the whole galaxy to settle down at about half the turnaround radius. And you can equate roughly the kinetic energy to the potential energy. Find the temperature by equating 3 kT by mu. Mu is what is called the mean molecular weight, okay, to the velocity squared. Get an estimate of the density. So you can put in numbers, all from the spherical model. These are not sacred, But they are interesting numbers to first start thinking about the whole subject. And if you put in these numbers, what you find is that if you have a dark matter halo of about 10 to the 12 solar mass, collapsing, let's say, at redshift of 2, that's what I've normalized it to. The virial radius is about 80 kiloparsec. 100 is what the number that we had earlier. The circular velocity is about 300 kilometers per second, which is a bit bigger than what we have for the Milky Way galaxy. The temperature, virial temperature, is about few times million degree Kelvin. And this is the temperature at which the gas is. Now, remember that even the interstellar medium in our galaxy is at a density of about 1 particle per centimeter cube, average. The stellar density is 1 gram per centimeter cube on the average, which is like 24 orders of magnitude larger. So when you want to form galaxy, you have to squeeze things like hell. I mean, the density that has to. And if you take a halo like this, you'll find the average density is about 10 to the minus 3 particles per centimeter cube. So you have to collapse like anything before you get even roughly kind of the density that you would be interested in. And then try to form stars. So how do you do this? This hot gas which has settled down has to cool so that it can collapse further, because it's now occupying the whole dark matter halo. If it has to collapse, it has to cool, because if it cools, it will lose pressure support, then gravity will take over and make it go down into the central regions of the potential. So how does it cool? Gas, if you look at ionized gas, I mean, this at this degree, at this temperature, basically the gas would be ionized. I will later talk about possibilities of different other cooling process when the gas is predominantly neutral. Okay? At this stage, there are various important cooling mechanisms. What do you mean by cool? Cooling means you take this kinetic energy associated with the gas and somehow lose it and become colder. How do you lose it? You can, for example, radiate it away. That means there must be some radiative processes which can help you to radiate away energy that you have acquired. These radiative processes, for example, important ones I've listed here. Bremsstrahlung. Probably you have gone through some discussion of radiation from charged particles. So whenever you have a charged particle, there are two ways it can get rid of, it can emit photons. One is, I mean, there's only one way, of course. One is when it's accelerated, okay? And Bremsstrahlung is the radiation which you get when a charged particle, here electron, gets accelerated in the field of a proton. So you have these protons or ions, and you have electrons. They whiz past these, they get accelerated, and they emit radiation. This radiation, if it escapes the system, will take away energy from the system. So this is one way in which you can cool the gas. You can also cool the gas if you form atoms, because whenever you have free electron and a free ion, and it recombines to form, let's say, a hydrogen atom, you will emit a photon. If this photon can escape the system, then that is another way in which you cool the system. So there is a recombination of hydrogen, and for primordial gas, there is also recombination of helium, because there is helium also which you have formed during the Big Bang nucleosynthesis. You can also cool gas in something called Compton cooling. That is, if you have radiation, okay, which is colder than the electrons that you have, then the scattering of the radiation against such electrons will lead to what is called the inverse Compton effect. It will boost the radiation frequency and take away energy. What radiation do we have? We have, for example, the cosmic microwave background radiation itself at sufficiently high redshift that itself can take away energy from hot gas. And something which you will come to a bit later If you have very cold system where such that the gas is not even ionized, so that you can't have so much of Bremsstrahlung, helium, or hydrogen recombination, you can try to form molecules, and these molecules can lead to emission of photons. So I'll come to some of these. The bottom line, which I will try to explain, is that the galaxy masses are set by the ability of the gas to cool within some dynamical kind of time scale. So this is a typical cooling curve that you will see in this, all taken from Barkana and Loeb. It's a review long time back again, 2001. Some of you may have been a few years old, I guess. Okay. Yes, so that's why I'm saying. So it's a very good review. If you want a bunch of references later, I will give you a bunch of references in a later slide. There is a very nice recent book. Recent means almost already nearly a decade old, by Moe, White, and Vanden Bosch on galaxy formation. Covers all kinds of stuff on galaxy formation, and none of the three are here, of course, but I think they have written a very up-to-date kind of book, and I would encourage people to look at it. There are, of course, older and older books, and there are a bunch of them which we can look at. Okay, so in fact, this is taken from that book, Moe, Vanden Bosch, and White. So these are called cooling curves, okay? What is plotted here is temperature. I mean, it is the same as this. I'll come back to this. Temperature against the cooling rate, okay? And normalized in a particular way. This is the amount of energy per unit volume in ergs centimeter cube per second. They're normalized in a way that if you take this lambda multiplied by density squared, you will give the energy per unit volume per second, the energy emitted by the gas per unit volume per second. Why density squared is important? Most of the processes, but all the processes which I talked about, depend upon square of the density. You have Bremsstrahlung, two guys have to come together and then scatter. You have recombination, an electron and an ion have to come together, so that they depend on the square of the density. So this is the canonical way in which people plot. For example, if you multiply it by 1 particle per centimeter cube, these are exactly the numbers. And you can see various features in this cooling curve. This part here, at large temperatures, is dominated by the Bremsstrahlung cooling. Because at those temperatures, there are no atoms. Most of the stuff is ionized completely. So it's only electron scattering of kind of protons. By the way, please feel free to stop me at any moment and ask whatever you want. I kind of generally advertise that you take care of yourself and I can take care of myself. Okay, so please don't. So this part is Bremsstrahlung cooling. Then there are these peaks here. At this peak is where hydrogen recombination line cooling is maximum. And at this peak is where helium recombination line is maximum. And the bottommost curve is for the primordial composition gas. There are no what astronomers call metals. Metals means anything other than hydrogen, helium. And these metals have to wait mostly for stars to form, because the stars synthesize heavier elements mostly, and then they have to be put back into the gas by something like a supernova explosion. So they have to wait a bit. They have to wait at least until the first stars form. Okay? So that's why initially one only considers this bottommost curve. But if you want to consider some enriched gas, for example, today, this Z equal to Z sun is today's abundance of solar abundance, then the cooling gets drastically enhanced. The cooling gets enhanced because now there are new channels of radiating away the energy, because of the fact that all these other, at high temperatures, there are high ionization states of, let's say, various things like iron, carbon, which can all lead to radiation of the energy. So you get enhanced cooling. Now, this part which I'll come back to, so you can see that there's a drastic cut at 10 to the 4. That's because atoms have formed. If you go below that temperature, there is no easy way to get rid of the energy by these processes like Bremsstrahlung and all that, because atoms have formed. And so there's no recombination possible now. There's no ionized particle to have Bremsstrahlung. Then that part has to wait for molecules to form. You can, today, for example, stars form in what are called molecular clouds, and I'll come back to that a bit later, where the temperatures are pretty low. They're much lower than this 10 to the 4. How do you ever get to such a temperature? You have to, this part of the curve is because of hydrogen molecule formation. And I'll come back to this a bit later. So given this cooling curve, you can calculate, given the density, given the temperature, you can calculate how fast the gas which has come to equilibrium in a halo can cool. Okay? And that's what's been done here. So this is a cooling curve. For example, this is an approximation which was probably introduced by Peacock long time back. And he was here, I think, last week. And it's also there in one of the reviews that we wrote long time back. You can fit such a model to this cooling curve. And if you take one of these branches, here I've taken this branch, T to the minus half branch. This branch is for high temperatures, the Bremsstrahlung. This branch is for the low temperatures. When you plug it in, how do you calculate? You can calculate the time taken for this gas to cool. The time taken is take all the thermal energy that you have, which here it is rho kt, 3 rho kt by mu. It could be 2 or it could be smaller than 1 depending upon the composition. Divide that by this cooling rate, which is all this lambda Ne squared. Okay? That is the time in which the thermal energy will be lost. And if you put in some numbers, for example, you take the same 10 to the 12 solar mass halo. How do I know the temperature density? I know it from the spherical model. I know the temperature from this. I know the density from the spherical model. Okay? And I've taken some fraction of 10% to be the amount of gas compared to the dark matter. Now you will take it to be whatever omega baryon by omega dark matter, which is more like 1/6. So this is also, could be a bit larger, larger than 0.1. And this is the turnaround radius. This is the halo mass. You will see that for this halo mass, the cooling time scale is a few billion years. And suppose you compare it with some kind of dynamical time scale, the time scale over which this collapse occurred. Okay? If the thing completely cooled, so I have taken T collapse by 2, it's also a few billion years. Gravitational time scale. In this particular case, it is just the time for which the fluctuation, spherical model fluctuation expanded and then collapsed. So you take the time scale over which it collapsed, which is why I've taken a factor of 2 smaller. So it's that time from theta equal to pi to theta equal to 2 pi in the spherical model, for example. And I put the numbers in again the same way, and I find about this. Now, if I take the ratio of this, the cooling to the dynamical time scale, I find it to be about 1 for a 10 to the 12 solar mass halo, and find it to decrease with mass, because this went as mass to the half, this went as mass to the minus half. Okay? And so smaller masses can cool faster than the dynamical time scale. Larger masses cool slower than the dynamical time scale. This seems to indicate some way in which you can get a mass for a galaxy. Because why should cooling be important? Suppose you are in a hierarchical clustering universe. So there are various kinds of arguments which people made. then each mass scale is going to collapse, and then within maybe Hubble time, one more mass scale is going to collapse on top of that, one more mass scale is going to collapse on top of that. Every time something collapses, the gas will get heated up. Now, if the gas is not able to cool within this time scale of collapse, and not able to sink, when it cools, it will sink to the center of the potential, it may form stars, at least it will become more bound. Then when the next stage in the hierarchy happens, you will not form stars because it is the same gas has now got heated up to even higher temperature. So this idea of comparing the dynamical time scale to the cooling time scale is fairly old actually. It's coming from a paper by Hoyle in 40s or something. Then very important papers by Rishi, Ostreicher, Silk in the late 70s. This was a suggestion that the reason that the thing which sets the galaxy scales, the physical reason for having scales of galaxies to be about 10 to the 11, 10 to the 12 solar mass, is that the gas which you have, which is going to form the galaxy, should cool fast enough compared to something. In a hierarchical clustering theory, it's compared to the time when something bigger comes and collapses on top of this. If it can cool fast enough, then this gas could lose pressure support, sink to the center, has a chance of fragmenting to stars. And I'll say how it can fragment to stars. If it cannot cool fast enough, then the next object which is going to collapse in the same region, bigger object, is going to heat up everything again to that virial temperature, which is even higher. And it will never cool after that. Clusters of galaxies, groups of galaxies, where you see X-ray emission from hot gas, which is a whole blob of gas rather than blob of stars of 1 megaparsec, are those guys which did not cool within the dynamical time scale. And galaxies that you see are objects which could cool within some dynamical time scale. So this becomes the first bit of message which I want to convey. Yeah. Yeah. Yes. Thank you. Yeah. That is this. Yeah. Yeah. Thanks. I'm sure Aseem knows the answer. He just wanted me to. Yeah. Well, there was once when I was in somebody's talk, and I think Narlikar, Jayant, asked him a question. And the guy was a bit struggling a bit. I said, yeah, this is the answer. So then Narlikar said, I know you know the answer. I want to know whether he knows the answer. So, but here it's ulta. You can see that this cooling is efficient here, right? I took this part of the curve basically, but below 10 to the 4 degree Kelvin, the cooling rate drops like anything. So this approximation which I used here, okay, this T to the minus half, is not correct because the cooling rate drops precipitously after that. Then the cooling time scale will become much longer than any dynamical time scale. So that is a smaller temperature of about 10 to the 4. If I go back and ask, when is it 10 to the 4 here, roughly, okay, it's like a factor of 100 here. And if I put 3 by 2 there, okay, so 100 to power 3 by 2 is 1,000. So instead of 10 to the 12, you'll get 10 to the 9. So roughly 10 to the 9, and of course, here I put, there's a factor of 3 also, which 3 to the 3 half. So you may get up to what Aseem said, 10 to the 8 solar mass object. So below that, if you take below about 10 to the 8, 10 to the 9 solar mass object, again the cooling rate, because the gas which you have captured, although it has got heated, it's not ionized. It's not able to do recombination line cooling. Again, the cooling rate has dropped so much that you will not be able to cool within dynamical time scales. And so this again sets a lower bound. So you have a range now, about 10 to the 8, 10 to the 9 solar mass halo to about 10 to the 12 solar mass halo, where cooling can be efficient enough for this gas to survive stages, higher, upper and upper stages of hierarchical clustering. That argument will again get slightly modified if you allow for molecular line cooling. And we'll again come to that. So the bottom line, as I said, is visible galaxy mass is set by the ability to cool within dynamical timescale. And you can do this a bit more in detail. You can draw this fantastically complicated diagram, which is also taken from Moe, Vanden Bosch, and White. The first time I saw this diagram was in a paper by Rishi, Primack, Blumenthal, something like 1984. And at that time, Paddy and I were trying to understand all this stuff. And we've spent a lot of time, what the hell is this thing? So the same cooling curve here has been drawn in a slightly different way. Now this x-axis is temperature, the y-axis is density. Once you have a density, you have a dynamical timescale, because 1 upon root 0 is a collapse timescale in anything. Okay? Once you have a density, you have some dynamical timescale. Once you have density and temperature, you have a cooling timescale. Because you know the rate at which gas can cool given some process. Okay? And you know it depends on density and temperature. So you can ask, when is the cooling timescale equal to the dynamical timescale? And that is this curve here. These two dips are corresponding exactly to the peak in cooling from hydrogen and peak in cooling from helium. This branch is because of bremsstrahlung, again at high temperature. And this other curve is when there are lots of metals and you have solar abundance and the cooling has become more efficient. And it has, the T cool equal to T dynamical has gone into lower density region and higher temperature regions. Because the lower the density, longer it will take to cool. Higher the temperature, the longer it will take to cool, the weight. So, this is the same curve as this, but now drawn as a curve showing equal dynamical and cooling timescale. Now you can read off various interesting things from this. What's also shown in these horizontal lines are the density that you expect for virialized objects, okay, at those redshifts, if they collapsed at those redshifts, roughly. So this is something collapsing at redshift 0 is collapsing at redshift 5. These lines are the density temperature relation of different mass halos, which you can easily find by saying, see, if you have mass is rho r cubed, okay, temperature is gm by r, use these two relations, and you'll find that the gas mass is T to the 3/2 n to the -12. So which corresponds to, in log T log n plane, a straight line. Okay? So that is this. This is 10 to the 15 solar mass. This is 10 to the 13, 12, 11, and so on and so forth. Whenever you are in this region inside here, the cooling is effective. The T cool is smaller than T dynamical. And so you can form, eventually, let's say, galaxies. Whenever you are outside this region, the cooling is inefficient. And then you can read off, for example, if something collapses at redshift 2 or 3 or whatever, or you take this 10 to the 12 solar mass line, okay, it needs to, sorry, this is 10 to the 12, right? This is 10 to the 12. Which one? This one. So you can see that this one is, cooling is effective, this one is on the threshold. I had put some rough numbers in that expression which I gave you. And here, for example, this cutoff is about 10 to the 8 solar mass here, okay? Provided it collapses by redshift 5. So again, the same message is being conveyed that if you can cool efficiently, then you can form galaxies. Now, before dark matter came on the picture, or before this kind of thing, the same argument was there. I mean, this argument has been there, I said, from 40s. There the argument was question of star formation. That unless you cool efficiently, you can never fragment to form stars. You can never form stars unless you cool efficiently. And if you go and see these different papers, one by Silk and one by Rees and Ostreicher, they make the argument also in a somewhat different way. In fact, the Silk argument has come back in a different way, and I will come to that. This is all very good. I have about 10 minutes or 15 minutes or something. 15 minutes. This says 9 minutes. Okay. So, this is fine, and this is where things stood until about 2003 or so. Then people realized that this simple picture that I have been advertising, that you have this dark matter halo which collapses, the gas heats up, and then you cool to form stars in the center, sometimes may not be the way things happen, because suppose cooling is so effective, then the gas collapses. Let's say it tries to heat up by forming a shock. Across the shock, the gas heats up, but suppose it cools very fast. Then before you even form the shock, the gas would just lose all its thermal energy, and you may never form this shock. So these two gentlemen, Birnbaum and Deckel, wrote a very interesting paper that it may be that you never, if you have to not wait for the gas to heat up and then look at the cooling, you have to do this at the same time. When the gas is heating, it can also cool. So they did a very simple spherical type of model. They did the normal stuff for dark matter. They just did shells of dark matter expanding and collapsing. They added some angular momentum, a softening. They solved this equation for shells of dark matter. For shells of gas, they included some pressure term, a slight angular momentum term. They solved the momentum energy equation, and also allowed for some viscous term to smooth formation of shocks. And they showed some interesting stuff. For the top panel is shown high mass halos collapsing. And whatever I have described there happens, whatever I described before happens. Shells of baryons or gas, they expand, they turn around, collapse, form a shock, and then they settle down to equilibrium, because they are now pressure supported in this potential. And the location where the shock is keeps moving outwards. This is what you expect. In the beginning, everything is cold, everything is not uniform density, so that they all arrive at the center at the same time. They have some density profile. Things happen first in the center, and you get hot gas being formed at the center. You get a shock there. Then you get more and more shells adding to this, and the shock will move out until all the baryons in the dark matter halo will get shocked and become hot. And the picture that I was advertising, that after this you think, now they can cool. This would happen for these massive halos where the cooling is not that efficient, it's just on the threshold. But for halos where cooling is efficient, smaller galaxies, what happens is that when it collapse happens, the shock tries to form, but it never really forms. Okay, the gas immediately gets cold. And again, the dividing line is roughly when T cool is T dynamical. So for smaller mass halos, the cooling never happens that first you get heated and then you cool. As you try to get heated, the gas itself cools. So this has been now known as a different mode of accretion of gas, called the cold mode of accretion. Okay? And it typically occurs at high redshift. So this is a later paper by Keres et al. At high redshifts for lower masses. So what is shown here is as a mass, and then this fraction of the gas which gets accreted in the cold mode, which is the solid line, and the hot mode, which is the dashed line. So at high redshift, there's a large fraction which never has to heat up to cool. Yeah, merger rate is not. No, here the gas is cooling without having to heat. It's trying to heat up, but the cooling is so efficient that the gas across the shock is already cold. Then you will never cool. That's what I said in the beginning. But the time scale for that to happen is the dynamical time scale, or some fraction of the Hubble time at that time. Probably something like 1/10 the Hubble time will be the dynamical time scale. The cooling time is supposed to be much shorter than that, then this will happen. You get this cold mode accretion. As you go to lower redshift, this is at z equal to 0, then only masses below about 10 to the 10.5 have predominantly cold mode, and the higher mass guys have hot mode. And of course, this cold mode accretion also has a different morphology. For example, in the same paper, they showed this. What happens to the hot particles and what happens to the cold particles? It seems that they will, see, the way the morphology, the accretion occurs is not just spherical collapse, right? You will have collapse to form filaments. The filaments will go to nodes. And the cold mode happens along these nodes. This, the bottom picture is one for the cold accretion. So there's a very different way in which the gas collapses, not by having hot gas first settling into hydrostatic equilibrium and then cooling, but some fraction of the gas cannot even heat up to shock because the cooling is so efficient. And there's another plot from Moe, Vanden Bosch, and White about the cold versus the hot mode. Again, the division is roughly at T equal to T dynamical, and things which are kind of on this side, lower temperature, the cold mode accretion is more predominant. The higher temperatures, the hot mode accretion is more predominant. Right, sorry, what did I do? I went faster, yes. So this also means quite interesting stuff. Because if you have cold gas coming directly and hitting, let's say, some object which is going to form a galaxy, it's going to stir up the medium a lot more. If you have hot accretion, hot gas collapsing slowly on a dynamical time scale, you will slowly settle into whatever object that you have. But you have these streams which will come and impact. Then it's going to create turbulence, it's going to create a lot of interesting stuff happening. So this was a very different kind of realization. So this is the story that the bottom line I wanted to actually stop here, but I can carry on a little bit more, is that you have one physical property which decides the mass scale of galaxies. And that is how fast the gas can cool. So this is the message. This is the only thing which you have to take out. Rest of the things you can go read papers, everything. And how the gas cools depends upon, at the higher mass end, the gas cannot cool because the temperature is too high compared to the cooling time scale is too long compared to dynamical time scale. At lower mass end, the gas cannot cool because again the cooling time scale is too long compared to dynamical time scale. But this can get changed, and this is the next thing which I wanted to get into. If you form other stuff other than atoms, and this is how the first stars may actually have formed. So let me, Aseem, I have 5 minutes or I should stop. Do you want to stop? Do you have questions? No questions? Then I'll carry on. You can prevent me by asking questions. Okay. Let me just say this. The other cooling, which I've neglected so far, is molecular line cooling. Now, to form molecules, you have hydrogen and you have helium. The most abundant is hydrogen. He's telling me to stop, but I'll carry on. The abundance of hydrogen means that the molecule that you can form is H2 molecule. But H2 molecule is not easy to form because you have two neutral hydrogen atoms. They have to somehow get attracted to each other. Now they are both symmetric completely. You have this S. I mean, the lowest orbit of electron is spherically symmetric. Everything is symmetric. If they come sufficiently close, they could induce some dipole moments. But otherwise, it's very difficult. So to form this molecule itself, in the interstellar medium, it's mediated by, firstly, electrons, and secondly, by having dust, in which things can happen. The way electrons do it is that if you take an electron, if you have electrons, they can attach themselves to hydrogen and form an H- ion. Now this H- ion, now things are no longer symmetric between the H- ion and the hydrogen atom. So they can combine together to form a molecule and give back the electron. So you started with this electron and you ended back with the electron out. So the electron is like a catalyst. So if you have enough electrons, then you can form H2 molecules at a certain rate. The more electrons that you have, the better it is. But after recombination, there are not so many electrons around. So it's a very slow process. And it depends upon what residual electrons that you have. And that means that any other way of creating electrons, for example, if you have some decaying particle which will do something to ionize stuff and create a little bit of electrons, I mean, you have some ionizing radiation from somewhere and creating some electron, will all increase this H2 formation. And then once you have H2 formed, then you can have a different mode of cooling. And that mode is cooling by, again, collisional excitation of now rotational levels. See, the electronic levels are pretty high in energy of hydrogen atom and all that. But the rotational energy levels have lower energy. So if you excite the rotational energy level and then come back, then you can emit photons again and you can get rid of the kinetic energy. Again, H2 molecule being symmetric, there are certain conservation laws. You cannot go down from the lowest rotational level, which will involve a dipole type transition, to the ground state. You have to go from J equal to 2 to ground state, which means you have a slightly higher energy than if you had pure molecular cooling. And the time when you can do that molecular cooling from a lower level is if you have a slightly asymmetric situation like hydrogen and deuterium, which you have a very small fraction. If they formed a molecule, which is the HD molecule, then you can cool by that. So what happens is that the reason now is that if you form a little bit of H2 molecule, then this part of the curve becomes relevant. That at lower temperature, up to about 1000 degree or few thousand degree Kelvin, even though you do not have atomic transitions, even though now you have fully almost neutral hydrogen in the gas, by forming this molecular hydrogen, you can cool the system and again do the same thing. Try to see whether you can collapse the gas faster than the dynamical time scale. And that will be relevant as I will start tomorrow for the first star formation. Because as you know, these structures are growing hierarchically, and we will start on this tomorrow. So this thing. Okay, thanks. So we'll see you tomorrow.